Hello everyone again. Today we are going to look at the significant figures, and after the lesson we are going to be able to show an understanding of the distinction between systematic error and random errors. Also, you are going to be able to identify the number of significant figures and the number of digits after a point. Let's start with the precision and accuracy. Accuracy is the closeness of agreement between a measured value and a true or accepted value. For example, the accepted value for the gravitational acceleration is 9.81 meters per second square. If you measure g as, for example, something like 9.22, for example, it is not very close to the accepted value, so there is some problem with the accuracy. So as much as it is closer to the accepted value, that much it is accurate. Second, the precision is the degree of exactness of a measurement. For example, if we measure the length of our table as 1.5 meter, or we can measure it 1.52 meters, or you can measure it as 1.524 meters. As you see, as the number of decimals increases, the precision of measurement increases. Let's understand it with an analogy. Here, if the arrows hit the center, it means it is accurate, and if the arrows are close to each other, it is price. So here it is neither accurate nor price, because they are far away from each other. Also, they did not hit the center. But in this case, in the second case, it is price but not accurate. It is not hit at the middle, but they are very close to each other. And as you see here, it is both price and accurate. All arrows are at the center and they are close to each other. Let's look at the types of errors. Random error has no pattern. There is no source. We cannot identify the source of the random error. You cannot predict random error, and these errors are usually unavoidable. For example, when weighing yourself on a scale, you position yourself slightly different each time, and each time you are going to measure a different weight. For example, when taking a volume reading in a flask, you may read the value from different angle each time, and since you are reading from different angles, each time you are going to measure different values, and they are going to be random errors. On the other hand, the systematic error is consistent. Always you measure similar or same error. It is a repeatable error associated with the faulty of the equipment or a flawed experimental design. These errors are usually caused by measuring instruments that are incorrectly calibrated or are used incorrectly. For example, measuring length with a metal ruler will give a different result at a cold temperature than at a hot temperature due to thermal expansion of the material. So for example, if you are measuring some length with a metal ruler on a hot day, it is going to be a little bit elongated. It will expand. So on a hot day, when you measure with a metal ruler, always you are going to measure more than 1 meter. For example, if this is 1 meter, and on a hot day you are going to always measure more than 1 meter. Let's start with the significant figures. The significant figures in a measurement consist of all the digits known with certainty plus one final digit, which is uncertain. I will expand this definition. Let's look at the examples. So here we have a rectangular area here. Assume now we are going to measure the length. We are going to measure this length of the rectangle. If this is our ruler, and here we are going to exactly know that it is 4 centimeters. It is 4 centimeters, and something here we are going to estimate it. This is definite. We certainly know that it is 4, and it is more than 4. Then we don't know this exact value, and it is going to be something like, for example, 4.3. So here these two digits are significant. One of them is known with certainty. We exactly know the length is 4, and some other values, for example 3, this is uncertain. It can be 4.2 or 4.3 or 4.35, something like that. We don't know. But if we measure with this second ruler, which also include some scaling in millimeters, as you see, now this is 4 is exact, and 4.12. It is between the length is this length is between 4.2 and 4.3. So in this case now we know In this case, now we know that the exact value is between 4.2 or 4.3. It is more than 4.2 and less than 4.3. We exactly know 4.2, and there is some, we have to estimate one more. For example, we can say it is 4.27, something like that. So in this case, we have three significant figures, and 4 and 2 are exactly known. Why? Because this is 4, 1, 2, and it is more than 2. We estimate it to be 7. So here we have three significant figures. Two of them are known with certainty, and one of them is uncertain digit. Okay, so the last digit in a measurement is always the uncertain digit. For example, in the measurement with this ruler, we measure 4.3. 3 is uncertain. It can be 4.2 or 4.25, we don't know. It is significant even if it is not certain. Here 3 is not significant. I'm sorry, 3 is not, it is uncertain, but still it is a significant figure. The more significant digits a value has, the more price the measurement will be. So measurement with this ruler, we have two significant figures. With the second ruler, we are going to measure 4.27, for example, and here we have three significant figures, and measurement here is more price. So let's look at an example of significant figure again. Assume you are going to measure this length. Now in measuring this length, you see here we have a 1, this is 1, and 1.1, 1.2, and this is somewhere between 1.2 and 1.3. It is something between 1.2 and 1.3, and assume it is 1.28 units. Here the first digit is certain. Certainly we know that this is 1, and also the second certain digit is 2. Why? Because it is 1.2. This is 1 and 1.1, 1.2, but the third digit is uncertain. It can be 7 or it can be 8. We wrote 8, and here, as you see, in this measurement we have two certain digits, 1 and 2. 8 is uncertain. We estimate the last one. So the significant figures are all certain digits plus 1 uncertain. Here all certain digits are 1 and 2, and plus 1 uncertain digit is 8. So we have three significant figures here. Let's read this measurement. What is the reading on the graduated cylinder? Which digits are uncertain? Now here is the meniscus. We know that 50 milliliter is certain, and 51, this is 60, this is 50, this is 55, so 51, 52, so 52 point, it is between 52 and 53. It is somewhere between 52 and 53. So as it is close to 53, so we know that two digits, we exactly know that the two digits are certain. It will be 52 point, for example, 8 milliliters. So here we have three significant figures. Two of them are certain, and one of them is uncertain. Okay, so here our measurement is going to be 52.8 milliliter. 8 is uncertain. Let's look at the rules for the digits, for significant figures. The first rule is, if a number contains no zeros, all of the digits are significant. For example, there are no zeros here. All of them are going to be significant, so we have three significant figures here. Let's look at the second number. It is 46.41. There are no zeros here, so they are all non-zero digits. That's why there are 4. And here 1.5. It is two significant figures. Here this is 0.693. Here we have three significant figures here. The second rule is all zeros between the non-zero digits are significant. Here 4 and 6 are non-zero, so this 0 is a significant 0. So the non-zero digits are already significant figures. 4 and 6 are significant figures. 0 is also significant. That's why there are three significant figures here. Similarly, here two zeros are between 2 and 5. Totally, there is going to be 5. And here two zeros between 8 and 7. Again, we are going to have significant figures. These two zeros are significant, so totally it's going to be 6. Next rule, the zeros to the right of a non-zero digit. The zeros to the right of a non-zero digit. So 3 is non-zero and 0 is at the right of the 3. this 0 is at the right of the 2, and similarly this one. So if they are to the right of a non-zero number but not sandwiched between non-zero and decimal point, they are not significant. As you see, they are at the right of the non-zero digits, so this is not significant. This is also not significant. These three are not also significant. So the number of significant figures for the first one is going to be 3 significant figures. Here only 1, here also only 1 significant figure. Next, zeros to the right of a non-zero digit again. If these zeros are sandwiched between a non-zero number and a decimal point, they are significant. So as you see, this 0 is at the right of a non-zero number, but it is between the decimal point and a non-zero number. So this 0 and that one, and here we have a decimal here also. This dot is very important here. If you have this decimal here, it means these are all significant. But if you don't have a dot here, it means they are not going to be significant. So it means here we have 2, 4, 5 significant figures for the first one, and 4 significant here, and there are going to be 5 significant figures here. Next rule, in decimals less than 1, for example this one 0.1, for example 0.09, zeros to the right of a decimal point that are to the left of the first non-zero digit are never significant. So they are at the left of the non-zero digit here. So they are zeros to the right of a decimal point. So this is the decimal point, and to the right of the decimal point, these zeros are not significant. So here for the first case we have only 1 significant figure. Okay. So in the second one we have 2 significant figures, and for the third one we have only 1 significant figure. So next rule, all zeros to the right of a decimal point are significant. Here is the decimal point, and this 0 is at the right of the decimal point. So here this 0 is significant. So the first one we are going to have 3 significant figures. If this value is not, for example, 0.50 I'm sorry 0.650, but if it is only 650, this 0 is not significant. But since we have a dot here, this 0 becomes significant. Again, this 0 is significant. This is going to be, we have a decimal here, 2 significant figures. Here we have a decimal, this 0 is significant, these are significant, and these are significant. So 4 here, 5 is going to be here, and 3 is going to be here. So you should be careful. Let me repeat, this is 1.10. 3 significant figures are here. But if it is, for example, 110, in this case, this 0 is not significant, only you are going to have 2 significant figures here. Rounding in significant digits. How we are going to, for example, round this number to 3 significant figures? We want to have only 3 significant figures. So 1, 2, 3. Now look at this one. Then look at the digit after the third digit. 1, 2, 3. We are going to concentrate on this digit. If this is bigger than 5 or bigger, then we are going to increase this one by 1. So this is going to be 401. And next number, this is there are 4 significant digits here. We want to round it to 2 significant digits. So as you see, this is 8, and now we are going to concentrate on this number. This number is 2 and it is smaller than 5, so rounding this number to 2 significant figures is going to be only equal to 8. We will not increase this one. If this is, for example, 7, in this case this is going to be 39. Next, let's round this one to 3 significant figures, and then 1, 2, 3, we are going to concentrate on this one. This is 5, and that's why we are going to increase this one by 1. This is going to be 100. I'm sorry, this is not correct. It's going to be 166. Okay, next one. Let's round this one to only 1 significant figures. We have 3 significant figures here, and rounding to only 1 significant figure, as you see, we are going to have only 1 non-zero digit here. Then please concentrate, look at this one. This is 8 and more than 5, so this number is going to be rounded to 0.03. And here we have only 1 significant figure. Please remember our previous rules that the decimals, the zeros between this decimal and first non-zero digit, they are not significant. That's why only 3 is significant. Okay, the last one, 2 significant figures, and we are going to look at this number. This is bigger than 5, so we are going to increase the second digit, and it's going to be equal to 99. What about the significant figures in addition and subtraction? The rule for the significant figures in addition and subtraction is they should be rounded to the same number of decimal places as the measurement with the least number of decimal places. An example will help us. Let's look at, for example, we are going to sum these three lengths. How many decimal places do we have here? 2 decimal places here. Here we have only 1 decimal place, and here we have 2 decimal places. This one includes the least decimal places. So 449.0 meters has the fewest decimal places, just 1. The answer must be rounded to 1 decimal place. Let's write all of them like this. 12.51, 449.0, 8.25. So if we sum them up, now here we have 2 decimal places, 1 decimal place, 1 decimal place. We should round it to only 1 decimal place, okay? After that, we should have only 1 digit. And now we see, as you see, after summation, we have 2 decimal places. Now we should round it, and in rounding, as you see, this is 6, and it is more than 5, so we are going to increase this one by 1. Our result is going to be 469.8 meters. Why? Because we round this one to here, this one becomes 8. What about the multiplication and division? The rule for this one is that round the answer to the same number of significant figures as the measurement with the least number of significant figures. An example will clarify this definition. Here we have 3 examples. We are going to multiply 7.55 with 0.34, and also multiply this one and also multiply this one. In multiplying these two values, let's look at the number of significant figures. Here, none of them are 0, all of them are non-zero, so 3 significant figures here. Here we have only 2 significant figures, this 0 is not significant. In multiplying these two values, if we multiply them, we are going to get 2.567. But we have to round this number to only 2 significant figures, so we are going to have 2 significant figures, and this number is 6 and bigger than 5, and rounding it is going to give us 2.6. For the second one, here we have 3 significant figures. This 0 is significant. Why? Because here we have a decimal, and here we have only 2 significant figures. This 0 is not significant, but this 0 is significant because this 0 is at the right of the decimal. And in making this multiplication, we are going to get 1.47. And here we have 3 significant figures. We have to round it to 2 significant figures. This 7 is more than 5. We are going to increase this 4 to 5. It is going to be 1.5 meters squared. Finally, in making this division, and we are going to get such a result. Okay, and let's look at our numbers. Here we have 1, 2, 3, 4, 5 significant figures here, and here we have only 2 significant figures. So our result also should be in 2 significant figures. But here, as you see, we have many. That's why 2 significant figures are going to be this one and that one. So in rounding this number, this is 1 to that one. This is less than 5, so it will not affect. So our result is going to be only 0.29. So here we have 0 to 9, but this is 2 significant figures because this 0, it is left of the decimal, it is not significant. Why significant figures are important? Significant figures are important to show the precision of your answer. No measuring device can make a measurement with 100% precision. Using significant figures allows the scientists to know how precise the answer is or how much uncertainty there is. In addition, the calculation result cannot be more precise than the measured result. For example, you measure your your mass as, for example, 70.6 kilograms, and you want to calculate your weight. This is your mass, and we know that weight is equal to mg, so it's going to be, we're going to multiply 70.6 times 9.81. In making this calculation, we are going to get 692.586. So as you see here, this has 3 significant figures, and this one also has 3 significant figures, but our calculation has 6 significant figures. So this shows that the calculation result is more precise than the calculated values, but this cannot be accepted. It cannot be more price than the measured value. So we have measured this one value, measured this value, and also this value. When you multiply, it seems to be more price, but actually it is not correct. That's why we have to round this number to 3 significant figures. So 1, 2, 3, we are going to look at this number. This is 5, so we have to increase in rounding. We are going to increase this one, so our weight is going to be 693 newtons. Okay, thank you for listening. See you next time.